Hello everyone, my name is Lodewijk Brand, and today I will be presenting a Primal-Dual Multi-Instance SVM for big data classifications. This work was performed jointly with undergraduate students, Lauren Zoe Baker and Carla Ellefson from the Colorado School of Mines, and Jackson Sargent from the University of Michigan. This work was advised by Dr. Hua Wang from the Colorado School of Mines. First, what to expect. I will begin with some motivation, first by introducing multi-instance learning and discussing their scalability. I will then follow this with our optimization algorithm, the design and implementations of our approach. This will be followed by a series of experiments exploring the performance and interpretability of our method on a computer vision dataset. Finally, we will end with a kernel extension of our approach and discuss some future work. So first, single versus multi-instance learning. In the single instance learning paradigm, a dataset X contains a series of columns that represent each instance within the dataset. In this learning paradigm, each instance is associated with a label. In the multi-instance learning paradigm, a dataset X is broken up into column blocks, xi, where each column block is known as a bag, and each bag is associated with a single label. Examples of this occur in image classification, where an image can be represented by a series of instances. Here we have an image of a bear that can be broken up into 4 patches. The goal of a multi-instance learning algorithm is to identify the instance within a particular bag that is representative or that is predictive of its label. Many applications fall under this multi-instance learning paradigm. Famously, Diederik et al. Use multi-instance learning for drug activity prediction. In this case, they have an active chemical compound within a drug that can be represented by multiple conformations. Each conformation is an instance within a bag. Similarly, this multi-instance learning paradigm has been extended to patches within images, sentences within documents, and patches within histopathological images. There are many more problems that can be formulated in this weakly supervised manner. Although in most of the literature associated with multi-instance learning, many authors focus only on this binary classification problem. This is primarily rooted in the fact that the data sets utilized only have +1 and -1 associated with their labels. In this work, we extend this multi-instance learning paradigm to K hyperplanes in this W matrix. Additionally, survey papers note that many of these multi-instance learning methods are not adopted due to their computational complexity requirements. This is because many of these SVM-based multi-instance learning methods utilize quadratic programming solvers to optimize their primal objectives. Here we have the primal objective for a multi-instance SVM. This is transformed into a dual problem and is then solved using a quadratic programming solver. This is done because the number of support vectors is generally smaller than the number of instances within your dataset. However, when the dataset gets very large, the quadratic programming solvers are slow to solve the problem. Motivated by the Weston and Watkins single instance SVM, we propose a multi-instance support vector machine that can be optimized without the use of a quadratic programming solver. We utilize the alternating direction method of multipliers by way of an augmented Lagrangian in our paper. Please refer to our paper for the detailed derivation steps for solving this Weston and Watkins multi-instance support vector machine. The derived Primal-Dual Multi-Instance SVM steps relies on solving a least squares problem, specifically with regards to the K hyperplanes in W, which has time complexity n1 through plus nn times the number of features squared. Thus, our approach, as derived in our paper, scales linearly as the number of bags increase. We want to extend our approach to deal with a large number of features as well. To do this, we utilize the optimal line search method initially proposed by Ni et al. In 2014 for single-instance SVMs and extend them to multi-instance SVMs. R's inexact scales linearly as the number of features and the number of bags increase. We compare our method against an array of popularly used multi-instance learning algorithms. As a baseline, we compare against a single-instance learning approach that assigns bags labels to all instances during training, and an array of other multi-instance learning algorithms that operate either on the instance level within a bag or some mapping that maps the entire bag of instances to a single instance using some sort of kernel function or some combination of the two. Furthermore, we compare our method against MINet and capital MINet, which are two end-to-end deep neural network architectures that have been used for multi-instance learning. Ours is the derived Primal-Dual Multi-Instance SVM, and R's inexact is the inexact variation using the optimal line search method to improve the scalability to features. We begin by exploring what happens when our algorithm is applied to an increasing number of bags. We can see that at around 800 bags, that our approach, both the exact and the inexact, train faster than the compared approaches. In addition, we want to explore whether our derived computational complexity of a linear scaling to features holds for our inexact approach. We can see here that as the number of features increase, that R's, the exact implementation, the training time increases quadratically, while our inexact approach continues to scale linearly to the number of features. This is the main contribution of our work, the linear scaling to bags and features. We test our approach against the Musk2, Fox, Elephant, and Tiger datasets, which are standard multi-instance learning benchmarks in the field. Additionally, we construct the MNIST bags dataset, which contains bags of MNIST digits and determines whether, and is trained to recognize whether a bag contains the letter 9 or not. We can see from this table that our approach, although it is not the best in every case, has comparable performance while having low train time. In addition, we compare our method to the SIVAL and SIVAL-deep datasets. In this case, from Ramini et al., the SIVAL dataset contains 60 images per class and 30 features per instance, while the SIVAL-deep dataset contains approximately 60 images per class, where each instance is represented by the 10th fully connected layer from an AlexNet network. We can see from these results that as the dataset increases in complexity, be that from number of classes, either 3, 5, 10, or 25, or by the representation of instance, that our inexact method is able to train within the time budget of 1,000 seconds. Finally, we explore the difference between the SIVAL and the SIVAL-deep datasets qualitatively. We can see from these two confusion matrices that features derived from a deep neural network architecture are also quite effective for multi-instance learning. We also work to interpret the results of the SIVAL and SIVAL-deep implementations. Since we can identify which instance is responsible for a particular classification, we can get insight into the effectiveness of our particular embedding for a multi-instance learning approach. This is one of the most effective uses, we argue, of these multi-instance learning paradigms. Finally, we note in our approach that our method is limited to data that is only linearly separable. We follow this primal-dual derivation to extend our approach to classify data that is not linearly separable and test on a synthetic data set where only the first instance within a bag is useful for predicting the class membership. Thank you very much for listening. The code and data for our approach are located on GitHub at minds-minds/pdMISVM.jl. The contact information for myself, Lodewijk Brand, and Dr. Hua Wang are below.